Okay, welcome. Today we are going to talk in more detail about how to actually implement these classification and regression trees using R. And this is the start of a code that I'm developed, and everything is going to be saved in this directory, which I have called trees. And there's a data set that I'm going to ask you to actually pull in, which I've attached to UB-Learn. So you'll have to save that to a folder and set your own directory and your own path so that you can access that data. And so I'm just going to start by running this. We're going to grow and prune classification and regression trees. I've decided we're going to use one particular package, which I think is the best package for doing this, and it's in a library called rpart. And so if you want to install this library, you simply need to install it from the CRAN repository using install packages, rpart. And the other library we're going to use is the MMST library. And we're going to use that because we will fit a regression tree to the Boston housing data and see how that plays out. But just to kind of get a feel for the different features, what I want to do is I first want to look in a little bit of detail into this library called rpart. And the reason I should make you aware that there's also a library called Tree, T-R-E-E, which you can use to grow trees. But I find the plotting to be a little bit awkward, and the plotting in rpart is much better. Now, this is really important because a lot of the interpretation and the nice aspects about these different trees has to do with visualizing the tree itself. And so from that point of view, although the tree package probably does well in the inference piece, rpart seems to be better in my opinion anyway. So if you want to check out Tree, go ahead. You can use Tree in your homework. You can use rpart. I don't care what you use. There are other packages out there that do regression trees. These are the two I'm suggesting. So just to get a feel for the commands, what we're going to do is look at a data set called iris. And there are actually, iris is a famous data set collected by Fisher himself, and there are many different packages that have this data because it's a classic data set for doing classification. And in this particular one, we try to classify different types of irises. There's different species, if you will. And according to some of these different predictors, the predictors have to do with measurements on the length of the sepal and length of the petal. And it's a very small data set, 150 observations. So I'm just going to call it in. And what I'm going to do is I'm going to look at the rpart function. And we're just going to talk about that for a minute before we get started. This is the function we're going to do the fitting with. This is recursive partitioning of a regression tree. And so here are the things that we need to input. And you can see that this goes by the formula syntax. So that's familiar to us. We have to insert the data set. There are some things we can do with weights. Okay, this is related to weighting a loss. So if you have to ever weight a loss in this case, you might want to look into that. And you can deal with missing observations. You can specify the model. And let me see here. This is the one that we're interested in. The method piece. These are kind of unusual. I'm not sure exactly that we'll ever need to set these things. But the method, the default method is for the regression trees. That's the ANOVA piece. But if we're doing classification, we have to tell it so. We have to specify the method as class. Survival data, we can use this exponential, and they also have this for Poisson data as well. So now let's see what else we need to know. One thing you're going to see here is a piece called control. And control is where you put in your options. So for those of you, with a math background, that if you've ever solved differential equations in MATLAB, we have to set all those options about the different tolerances and the methods and stuff. The control here is very similar to that. So we feed it a bunch of options. But to understand the control, we're going to just click on this link here, and it's going to take us into things that will look familiar to you related to our lecture. How are we actually going to specify the parameters? So there's different things that we can do to ensure we get a rich tree. Okay, because remember, we want to kind of grow the tree out big and then prune it back. One is specifying, in this case, the min split. That relates to the minimum number of observations that must exist in a node in order for the split to be attempted. So if there aren't enough data points in that particular observation, then it's not going to attempt a split. The min bucket has to do with the terminal nodes, in particular the minimum number of observations that has to be observed in any terminal. So you need to see, you don't want to see a tree grown such that there's less than 3 training points in a terminal node. That's an example. You might just say it's 1. It doesn't really matter. Remember, as long as it's rich enough. So a lot of these are a little bit, not so. You don't have to be very serious when you kind of set these. You just want to kind of grow a rich tree. So CP is the Marrow CP statistic, or the complexity parameter they call it in this case. And here, remember how this relates to goodness of fit, and it's the same thing. Now when you specify CP here, this is actually, it's not the CP itself, it puts a, let me say a bound, if you will, a lower bound, on any splits that are attempted further down the line. So if you've split the tree 3 times, you're going to see the CP kind of, you improve your goodness of fit, you improve your goodness of fit, you improve, and then all of a sudden you might not see any improvement at the next step. And so this threshold gives an improvement. You have to improve by so much if you want, things to get better. So you can set this. And setting it to be a value like 1 or 0.1 or it requires that in order for us to keep splitting, we need to see improvement. If we stop seeing improvement or we see very little improvement, then we're done. We're not going to split anymore. So we can actually choose this parameter by, so here they describe it. The main role of this parameter is to save computing time by pruning off splits that are obviously not worthwhile. We can select this using cross-validation. If we want to, we can set it to be 0. And if we see 0, that means that it doesn't matter, CP doesn't really matter. We want to just keep growing. So we're going to actually set it to be 0. Okay? And I'll show you then that we can still figure out this. I think I'm probably confusing a lot of people now. We'll see a plot of this where we can actually get a profile of CP, whereas if we set it to be too stringent, we're only going to see part of that profile. All right, and so there's some other more sophisticated things. A max depth is another thing that we can set. The surrogate stuff has to do with missing values. So these are all of the different options that have to be set. Now, what we can do is I'm going to describe a variable, a control sequence, if you will. Using this rpart.control, I'm going to set the parameters. And I'm just going to say the min split is 5. Let's see what else is here to set. Okay, the number of cross-validations in this case is 10, and I think that's okay, but I'm going to just set it to be 10. Now, if you don't set it, this is the default anyways, but I'm just going to put it in here as being one of the important parameters. CP I'm going to set to 0. I don't want it to be 0.1 because I want to see everything. Even if there's hardly any improvement, I want to see it. So this is a quick method. There's no sense in changing this. Now what I want to do is fit iris. And to do this, I'm going to use our part. And now I have to understand, okay, I actually understand that, but I need to see the names of the variables. Okay, species is the variable. And I'm going to use all of the data, all 4 of these predictors. And it turns out, if you've studied this data set, you know that these are actually the important ones, and the petal is less important. But the data I'm going to use is the iris data. The method, I have to tell it's a classification. And for the control, I want to pass it the parameters from model.control. Okay? So let's see what this looks like. Oops. Species is not found. Interesting. Oh. I'm not sure why that happened. I must have been using it from the wrong package. So let's see. Type. Okay. Let's not call it in again. Let's just do it like this. Okay, so now it seems to understand. So now, what happens here? We've already fit the model. Okay. If I do summary, fit iris, I'm not going to come up with too much. There's a lot of information here. Names, fit iris. We'll see all of the stuff that comes out, and we can there's a lot of information here that we talked about, so for example, variable importance, we can certainly do that also with a single tree. We talked about it in terms of a random forest, which is, over on an ensemble of trees, but we could look at that if we wanted to figure out what the most important variables are. We can also see that from the tree itself. CP table, this is an important table that we're going to look at a plot based on this table. And if we actually look, we can see all of the different rules and the improvements that occur. And we can also see at the end the different class counts. Now this is a lot to look at in this format, and it's not exactly pretty, but it gives rule-based information here. So if I look at, I encourage you to take a moment, hit pause, and investigate some of these different fields. Okay, so here are this is some split information, and also the counts at each one, improvement, and I'm not sure what this ADJ stands for. The CP table is an important one. Here we have different CPs, which we know are going to kind of decrease along the way. Here we have cross-validation error, and here we have relative error. I'm actually going to encourage you to use the cross-validation error itself. And what we're going to do is we're going to plot this error next and take a look at, actually I think we'll leave this for now. Let's plot a tree though. So I'm going to hit X11, and you can plot the object fit.iris. And now I'm going to set some things. So if you do plot.ourPart, you can get the information about the plotting, and there's some information here regarding how you want to visualize things. So I'm going to say I want uniform display, and I want to compress information. And now I need to tell it what I want to print. And so if you go through this plot file, you can kind of get an idea through their example, but I'm going to give you a better example that you can hopefully recapture some of these things, because there's really not much here in terms of examples. You can see text R part. This is where this pretty digits, all of these things come into play. So there's a lot of flexibility. So I said that this plot's better than the tree package. It's true, but it requires a little bit more in terms of setting things up. So all I'm going to do first is I'm going to fit iris. The text is going to take it from the object fit iris, and I'm going to kind of shrink the text down, otherwise it just gets kind of too big. And let's plot this and see what it looks like. Oops. And it looks like I messed that up. Okay, now let's try. Okay, so this is what the tree looks like. You might say that doesn't look too great in terms of visualization, but this is R, so it's okay. What we see are, as I mentioned to you, petal length and petal width are the most important variables. We didn't see anything about sepal coming into play here. And we also see all of the different things represented here. Setosa, versicolor, and virginica. All the different species are represented. And what's labeled here in the terminal regions, that's the from a majority vote. If you landed in this bin, you would be called versicolor. So this is one way. Now I just want to make this, all I'm going to do is copy and paste. I want to plot the same thing, but I want to kind of pretty it up a little bit. So here I'm going to say use.n is true, all is true, and for CEX, again, 0.5. So I'm using some commands within this text. So I showed you how to access that. And now I've displayed, through studying those commands and using them, a little bit more information. So here are the threshold points, or the splitting points, as you can see. And also what we have in the terminal nodes, although you really have to put your glasses on, and I don't have glasses anymore, my son just broke them. So what we have here are the indication of purity at each of the regional nodes. So here, 50 are Setosa, 0 that ended up in here from that data set are versicolor, and likewise, for virginica and so forth. So we can do that, and you can kind of figure out that this is versicolor because this is the majority. This is at that splitting point. This is mostly versicolor. This is also a versicolor bin because this is a majority is 47, and that's the label. So you kind of have to figure out what is what. But this is another visualization. And I think I've frozen things. I better save this. I'm going to call it Grow and Prune. This is for 2014. Okay. Now, sometimes things freeze up and I have to use a graphics off. And I hope that takes care of it. Okay. All right. And now, I think I was going to show you one more. Let's see. We can do a different plot if we want to kind of change what the branch looks like. I'm going to keep all of this the same. I'm going to add the command branch, and I'm going to kind of make the branches look different. Okay, so it gives a different, style of plot. The tree looks a little bit different. It's a little bit easier to interpret. So it's just, your preference. There's a lot of flexibility here. So maybe actually I shouldn't have shrunk in this case because this is such a small data set. What I would, try to kind of think about is, yeah, see, you can play. You can see the 0.5 was a little bit too small. 1 is a little bit too big. And so, and of course when I go like this so that you can see it, it looks even worse. But on my screen like this, it looks okay. So it takes a little bit of finessing. Okay. So now what I want to do is I want to grow a regression tree and prune it. So let's see here. And so here we will actually grow a classification tree and prune it. Okay? All right. So for this one, we can do load. There's an R data file called digging data.rdata. Okay. And here we can actually load the data. And so the data is called, let me see what's in the space here. It's called digdats. Okay. Okay, so for this one, I'm going to do the same thing, but I'm just going to take it just a step further and actually do some pruning. So for the iris data, it's kind of not interesting. I just wanted to show off here how to do some interesting plotting. And now I'm going to kind of focus on the model itself. So I'm going to copy and paste. So this digging data, if you look at head dig dats, it looks like this. It's got a response. It's got all of its predictors. And I think it has to do, I can't remember actually where this data came from, but I think it has to do with zoning and somehow some kind of there's some geographical interpretation here. I'm not exactly sure, but these stand for different zones in a particular region. We can set the model controls like this if we want to. These can certainly be the same. You might want to change this. I'm going to call this fit.dig. And so the R part model is going to be using all of the data, fitting the response, and the data is digdats. Okay. And so here, let's run this, and it ran fine. And now, instead of looking right away at the tree, what I want to do is I want to kind of just look at the profile of the CP statistic, or the cross-validation error, actually. And to do that, I'm going to look at the fourth column of that CP table, which I showed you. And I'm going to label this plot CP for model selection. And the Y label is going to be CV error. Okay, so let's just see what that looks like. Oops. I always do this, where I write something as a decimal point and then I use an underscore later. Okay, so here it is. It looks really nice. We have our cross-validated error here in our index. And so what I'm going to say here is it's pretty obvious that we would kind of want to stop at 10. Okay? And so each one of these corresponds to a tree. This is the complexity of the tree. 10 is the the index of the particular model. So if I look, how do I access that? So let's see here. One thing I can do is I can say min CP is which.min is fit dig cp.table 4. Okay? And it tells me, oops. Oh, this should be a regular table without a dot. Here I have min CP. It's the 10th one. So there we could count, but you'll see in the Boston one we won't be able to count. And so the prune tree, I'm going to call it prune fit dig. This is going to use a command called prune. Okay, so and we're going to prune it back to this model because this is the best model. I'll show you how to do that. So if I do help prune, this is the idea. It's recursively snipping off the least important splits based on complexity parameter CP. Okay, so a word here. I want to say that we talked about how to prune. And so this is a version of cost complexity pruning that's implemented. And we're actually growing and pruning based on this statistic that we're used to dealing with. In class, we talked about growing and pruning according to a cost complexity method, but that was largely driven by we had to designate what type of impurity function we were going to use. Now this one does not rely on an impurity function. This relies on just goodness of fit. Okay? If you go to the tree package, there you have an opportunity to look at changing the impurity function. Here you don't have that kind of flexibility. So, now that I mentioned this, I will at the end, I'll show you what I mean by that. I'll go to the tree package and I'll show you what I mean by that. And we'll talk about some of the different advantages to using those. But for now, we will prune according to the CP. And if I tell it, I just have to tell it the cost complexity parameter to which we're going to trim to. And that's the 10th one. And so if I look, I know it's the 10th one. I have a couple options. I can count down and tell it I want this one. I could copy and paste it into the function. Or I could use this and say I want to prune the tree. And the tree I'm going to prune is called fit.dig. And I want to prune it to, I could copy and paste this, or I could say fit.dig CP table. It's the first column, and the row is min CP, right? Because that's how I'm detecting it. So that's just a little bit more automated. I try not to rely on numbers so much, and this, if we change something now, we can just actually find them in CP. We should have a prune tree at this stage. Okay. Now what I want to do is I want to plot the full tree and the prune tree. Okay, so why not start with X11? And let's plot the simple one first. And I'm going to plot pruned fit dig. And, sorry about that. And I like the branch to be 0.3. You can use branch whatever you want. And I'm going to compress so it's easy to read. And for the title, I'm going to call it prune tree. Now, I'm going to do, for the text, I have to tell it that it's prune fit dig. And I don't want everything displayed. I just want the text to be shrunken down so I can read it. Okay, this is the prune tree. Looks nice. What I can see is there were 10 different, splitting points, and I can see, they're kind of represented here. And actually, if you looked at the classes, I think there were nine different classes there. So we would have to look to see if everything was represented, and it might not be, and that would be okay. But this still looks like a fairly complex tree, but remember there's a lot of different classes. So now let's copy and paste this and see what it looked like against the full tree. And so the full tree was called Fit Dig. So all I have to do is change this. And let's put them side by side. Except I'm going to call this the full tree. Okay, so we can see that this is obviously, grown pretty thin. Okay, it goes on and on. This is the optimal tree based on cross-validation. And so you'll notice that the structure, this is a subtree of this tree, and we talked about that. Okay. All right. The last thing I want to do before I show you the other function is to look at growing a regression tree. Now we're using a package called rpart, and it's built for regression trees actually. But so far we've only considered qualitative responses. So let's go ahead and load in the Boston data. Since we've used it so many times, I think it's nice to see it done with different methods. And I'm going to set the model controls for this data in the same way. I'm going to say xval is equal to 10 for the cross-validation. The min bucket, I'm going to say it has to be at least 2, which is pretty small. Okay, this tree is going to be grown out pretty big if that's the case. And that's fine with me. And I need at least 4 there to make a split. Again, it's going to be grown out big. It's fine. The other thing I want to say is that CP is equal to 0. Now I have these in some relative order that makes sense to me. This is the way it's displayed in the help file. You can move these things around as long as they're labeled appropriately. And so let's kind of run this first. And I just want to take a look again at the Boston data. Now we see here that this data is a little bit richer than the digging data in that it's not this binary data. We also see, and also too, the iris data, which is obviously the simplest one. We see there's different types of variables present here. And of course we're interested in predicting this MEDV column, which is the median value of a home. Now, we're going to do it in the exact same way. So we're going to fit Boston, rpart, really easy. We're just changing the data set, MEDV, use all the data except for that response column. And the controls, I'm going to call model controls, which I just wrote over. Now I'm going to actually go a few steps ahead here without running this. I mean, I'll run this and it will run, but I don't want to look at anything yet. Uh-oh. Okay, I had to take a little pause there because I had a bug, and it happens to me all the time. But here I misspelled the word control. Forgot my R. And now if I run it again, I should be fine. Okay, now that's good. Let's do the same thing that we did before. So I'm going to say which min is the Fit Boston CP table 4. Okay? All right. And I can also do a pruned fit based on whatever value that is. And I'll use Fit Boston. And for my CP, I'm just going to put in Fit Boston CP table. I'm going to use the row which corresponds to the min CP, and the CP is in the first column. So now I've done all of this. Now let's look at some plots, okay? We've done all the work here. So now what we have to do is we have to plot the tree. And so let's start, actually let's not plot the tree quite yet. Let's plot the CP, the error, the cross-validated error first. So here, this will be easier. If we fit Boston, and we're looking at the CP table in the first column, sorry, the fourth column that corresponds to the cross-validated error. And for the main, I'm going to call it CP for model selection. And the Y-lab is CV error. Okay. Okay, you can see that there's a lot of complexity here, a lot of different models. It's a richer data set, but we can see there's kind of a clear minimum here, and I'm just going to grab that minimum wherever it is. And I know actually that if I look at min CP, it's the 19th one. So there's 19 models here, right? So the 19th one is the optimal one. So we want to tell it, and we did tell it, and we pruned according to cutting back to that 19th model. But I want to take a look at the unpruned and pruned tree just to get an appreciation here of what happened. So first we will plot the pruned Fit Boston. And you know what I'm going to do is I'm just going to actually copy and paste these. Pruned Fit. I'm just going to re-enter the appropriate. So here, Pruned Fit Boston is the object we were interested in printing, but I want to keep all the settings the same. Okay. I liked the settings. And so here we can also use the Fit Boston as being the big tree. Okay, so now we're okay. Now, so we saw the model was kind of rich. Let's just see what this looks like. Wow, this is really bushy. This is what you call a bushy tree. You can see there's just a ton of stuff going on here. We grew it out really big. And this is a subtree of that bushy tree, which is optimal in this case based on the cross-validated error. Now, one thing that I did not show you, so let's look at the tree first. We can see, first of all, this is a subtree of the full tree, and we can see that RM, which is the number of rooms in a home, is the biggest indicator of the median value of a home. We kind of know that. And we see that it splits on it first, and then splits on it again, and so forth. LSTAT is another important indicator. We knew this also. If you remember when we did the original regression with this data set several labs ago, we saw the same important variables. So we get an idea, then crime rate, and so these are the important variables. Probably they're all represented here. It would be interesting to look at the overlap with the original set of variables to see which ones kind of are retained and if any are even eliminated. And what we see here at the terminal nodes are the actual values. So if you were to sprinkle new data down a tree, which I didn't show you how to do, but if you follow that through, you're assigned a value. And that value is determined according to the average of the training data, which in this case was the whole data set because we didn't split it. But it gives the average of those so there's going to be more error. There's more error in a regression setting because, it's assigned a specific value. So when you look at the residual sum of squares, it's going to be a little bit higher. But here we retain a nice structure. It's very easy to interpret. And that's kind of the way that we approach it. And so now I can see my machine is freezing up again. So I'm going to go here and do my trick, which is graphics off. So that full tree was kind of like R is complaining now because it's really bad at plotting and it doesn't like to plot all of these details. So it kind of gets into a freeze up defensive mode. So we want to save often when we're doing this. And the other thing that I didn't show you, because I really trust that you can do this at this point, I showed you the basic features of our part. I didn't talk to you about predict.rpart, but I don't want to go through it because it's really redundant with the other things that we've done leading up to this lab. But you can divide your data set into training and testing. You can hold out the test set, and do all the training and even the cross-validation using the training set to pick your complexity parameter. Then you can bring in the test set kind of as a validation set. Using this predict function, we can actually put in the object in a new data set, and it will give it the response variable. In this case, in a vector, or it will give a class or a probability of a class. There's some other fancy things here that it can do. So, vector, this is for regression trees, and so if we were to, one thing that we could do is we could actually, if we wanted to demonstrate this function, we could use predict. This is the training set prediction, which is we didn't divide it, so I think you understand that point. We didn't divide it, but we'll give it the fit, and the fit we're going to use for the prediction is going to be the pruned tree. And the new data is not really new. It is just the Boston data. And so let's see where the training points fall. So if I do pred train, I see all of these values. And so you'll see here, if I look at unique pred train, that there's the number here of unique predictions corresponds directly to the number of terminal nodes because of the way things are assigned in a regression tree as being the mean. So there's if you count them, 16, 17, 18, 19, there should be 19 terminal nodes here, and you'll see that, each one of these corresponds to one of those. And so every prediction, everything that's sprinkled in the top of the tree gets an assignment of one quantitative value, okay? But there's only 16, 17, 18, 19 different unique ones corresponding to the 19 regions. So if you wanted to, you could, and I think if you don't understand this point, you can come to see me, but you can divide into test and training. You can do prediction on the test set to get an idea of the test error if you wanted to compare that. You can certainly work with the cross-validation error to choose the pruning level, and that's definitely reasonable. So what I'm going to do is I'm going to stop here, and I'm going to record a small second segment which will correspond to the work with the tree library. And I'm not going to spend a lot of time on that. It's going to be optional, but I'll just show you some of the features there. I'll probably use another data set to show you a quick example in that language. Okay.